Next in chapter 15, let's talk about sampling distributions. So the law of large numbers assures us that if we measure enough subjects, our sample statistic, our population, our sample mean, X bar, will eventually get really unknown to our close to the unknown population parameter mu. If we took every one of the possible samples of a certain size, calculated the sample mean for each, and graphed all those values, we'd have a sampling distribution. So I'd be graphing the means of a whole bunch of different samples, and eventually this would approximate a normal curve. So when we use software to imitate chance behavior to carry out tasks such as exploring sampling distributions, this is called a simulation. And the population distribution of a variable is the distribution of values of the variable among all individuals in the population. That's our population distribution. But the sampling distribution of a statistic, so in this case of a mean, right? A mean is an example of a statistic, is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So let's look at this. But first, be careful. The population distribution describes the individuals that make up the population, and a sampling distribution describes how a statistic varies in many samples in the population. So here we've got our population sample, right? It's like more spread out, right? And this would be our true population mean. But the sampling distribution describes how sample means vary in repeated samples. So it's going to have less variance, it's going to be a little taller, but it still should fit a normal distribution. So when we choose many simple random samples from the population, the sampling distribution of the sample mean is centered at the population mean and is less spread out than the population distribution, meaning it has less variance. So its standard deviation is less. How do we calculate its standard deviation? Well, let's let X bar be the mean of a simple random sample of size n, drawn from a large population with a mean mu and a standard deviation sigma. What we do for the standard deviation of our sample mean is we're going to take sigma divided by the square root of n. So divided by the square root of our sample size. So because the mean of the statistic X bar is always equal to the mean of the population, that is, the sampling distribution of X bar is centered at mu, we say the statistic is an unbiased estimator of the parameter mu. Note that in any particular sample, X bar may fall above or below mu, but the graph of this sampling distribution will be centered at the population mean. So let's look at an illustration of this. So here we have our population. They have a mean of 25. Maybe we'll make it their age. It's a very young population. I could take a simple random sample of size X, a size 10, and get a mean of 26.42. I could take another simple random sample and get a mean of 24.28, and another simple random sample and get a mean of 25.2. So like here we had our true population mean was at 25, but I got some values of like 26, 24, really close, right? So this would be a good kind of visualization of our sampling distributions. We are graphing the means, and they do take on that normal shape. So because the standard deviation of the sampling distribution X bar is sigma over square root of n, the averages are less variable than the individual observations, so there's less variation. Not only is our standard deviation of the distribution of X bar smaller, it gets smaller as we take larger and larger samples too, because we're dividing by the square root of n. The results of large samples are even less variable than the results of small samples, but it's still less variable than the population. Although the standard deviation of our distribution X bar gets smaller, it does so at a rate of square root of n, not n. So to cut our sampling distribution in half, for instance, like the standard deviation in half, you'd have to take something 4 times as large, because like the square root of 4n would be 2n. So not just twice as large. The woes of math sometimes. So the last thing I'm going to say about this before I stop this video and we start talking about the central limit theorem is we have described the center and variability of our sampling distribution with sample mean x bar, but not its shape. The shape of the sampling distribution depends on the population distribution. So there is a simple relationship between the two distributions. So if the population distribution is normal, then so is the sampling distribution of the mean. And if individual observations have the normal distribution mu sigma, then the sample mean x bar of a simple random sample of n has the normal distribution mu, but my standard deviation changes to be divided by square root of n.